Hamburg, and he will tell us something magic. Okay. So I'm a theorist. And I have to give a talk about an experiment. Everybody's excited about it and nobody understands. So maybe I need a little encouragement before I start. Title, how to make a room temperature superconductor with light. Okay, so first of all I should answer the question, what is actually a superconductor? And of course you've all seen it. This works. Okay, here we go. Okay, superconductor is a thing that levitates above a magnet or vice versa. And more importantly, it is a superconductor, so it conducts without resistance. It also expels magnetic fields, so the superconductor and the magnet really don't like each other, therefore they levitation. But really, that's not so intuitive, right? So a superconductor actually, you should think of as a charged superfluid that flows without resistance. Still not so intuitive. Maybe it helps. Without resistance. Alright, more seriously though, from a point of view of optics, what is the optical property of a superconductor? So, here I'm showing you the optical conductivity, and really this is, I need something better here. Which is the coefficient between the current and the electric. Please point here, yeah? Okay, great. So, this is what you learned in school. R is U divided by I. This is just Ohm's law, R, U, D, I. Or if you need to memorize it, UDI. So what does it look like? A superconductor has an energy gap, so there's some, if you plot this as a function of frequency, there's an onset of excitations above the gap, but more importantly, it flows without resistance, so at zero frequency you have a Dirac delta function, and that comes along with, in the imaginary part of the optical conductivity, a 1 over omega divergence in the imaginary part, and basically this is the hallmark of a superconductor, the delta function and the 1 over omega. Alright, so the weight of this delta function peak in the real part and the divergence in the imaginary part measure the superfluid density from the point of view of optics. And so really the divergence here, this is the indication that we have a superfluid. So now, motivated by Rudi Völler, the experiment was performed on soccer balls. carpets on the walls or hockey balls. On an FCC lattice, you need to dope with some alkali ions in order to provide the electrons that can carry the supercurrent in the material. And if you do this in equilibrium, these materials are known to be superconductors in equilibrium. And in particular here I'm going to focus on the K3C60, which is one of these compounds. And you can see that it has an equilibrium TC of about 20 Kelvin. So far so good. And how does the equilibrium phase transition look like from the point of view of optics? Well, you see that if you go from the metal to the superconductor, then basically you go from a resistance that is not perfect to a perfect resistance, a perfect reflectivity, and this is basically, here you should see a perfect reflection of the laser pointers that they're pointing right there, so they will come back into your eyes. Be careful. Alright, so the real and imaginary part of the optical conductivity can be calculated from or can be extracted from this, and you see that you open a gap in the real part, as I explained before, and you also get this 1 over omega divergence in the imaginary part. This is how you go from the metal in red to the superconductor in blue, and usually you have to cool down in order to achieve that. This is the hallmark of the superconductor. In principle, there should also be a Dirac delta function here, but notice that if you do this at finite frequency optically, of course, at zero frequency, you never see the Dirac. Alright, so far so good. This is all equilibrium. I promised you room temperature, and of course now you might say, this is not room temperature, 20 Kelvin, you need liquid helium to cool it, it's really, really cold. Good. So, light-induced superconductivity. We need to come to the rescue and help these guys a bit to become superconducting at higher temperature. So how do we do that? We irradiate the material with lasers, we drive certain modes in the material, and maybe that helps it become a better superconductor. And in fact, now this is a result that was already published in 2021 in Nature Physics, in which they showed that by irradiating a material, the K3C60, with 40 terahertz excitation, they induced superconductivity, more precisely the optical response of the superconductor, at 100 Kelvin. Okay? And what's more, and this is illustrated here by this hourglass, is that this state turned out to be metastable, which means that a picosecond pulse then led to a nanosecond lifetime of this light-induced superconducting light state. Yeah, I would also be complaining about all these stupid laser. Alright, so, 100 Kelvin is still not really room temperature, but at least you can go from cooling with liquid helium to cooling with liquid nitrogen, so you can use the fancy molecular kitchen. And maybe some of you are able to achieve that in their labs very easily. Still, maybe room temperature in Antarctica for these guys, but not really for us. Maybe I shouldn't be so fast, right? I mean, depending on how the situation develops with the gas and so on, we don't really know how warm our rooms will be in this winter. That's not so funny. So what's new in 2022? Don't laugh, please. So the new thing that comes out this year is that now they've changed the setup. The experiment that I mentioned before was pumping at 40 terahertz. Now they can pump at 10 terahertz. This is the sigma-1 spectrum of the material in equilibrium, and you see that basically before they were pumping here, and now they are pumping at lower frequency down there. So they moved the pump from the excitations above this pump here to below, and maybe something new will happen then. Right? So this is what the data look like. They find at 100 Kelvin again, a situation where they increase the reflectivity to almost 1. They find this gap in sigma 1 and this depletion of spectral weight in the gap, and they find the upturn in sigma 2. So far so good. Now they can extract a measure of this effect, and more importantly, now they show this as a function of the pump fluence. Yeah? So basically, the pump fluence here that was needed in the old experiment is more or less the fluence of this guy here, whereas the fluence that is needed in a new experiment is one, does somebody have a really weak laser pointer, like one that, exactly. So here, now this can be achieved with a weaker laser pointer. So they see basically the reflectivity going to 1 already at a lower laser fluence, the gapping out of sigma 1 and the divergence of sigma 2. You can see that it already happens at below 1 millijoule per square centimeter, where before they needed more than 10. So this is quite nice. So this means that now, if they now plot this so-called photosusceptibility, which is a measure of how efficiently they can drive the system into the superconducting state, they find that this strongly peaks at around 40 milli-electron volt or 10 terahertz that I mentioned before. So this is the terahertz magic that was announced in the title, and importantly, this effect still persists after 10 picoseconds. The compounds are much shorter than that, and still at 50 picoseconds, you see that, notice this is a log scale, yeah, if you're still so aware at this late time in the evening. So basically the efficiency is now increased by 100 times compared to what was published before for this 10 terahertz pulse. Alright, so this is the superconductor, again, the superfluid. I can plot this now differently. I'm plotting here a quantity which is more or less the resistance of, that would correspond to the equilibrium resistance in a transport experiment. And again, you can see pumping at high frequency, you need way higher fluences to bring down the resistance, whereas at the smaller laser photon frequency, the resistance is already pushed down to zero with way lower fluences. And this is great. However, this is still at 100 Kelvin. So what about room temperature? Anybody have a guess? Am I going to show that it actually goes down? Let's take a vote. Who believes that I will show some room temperature? Okay. Who doesn't believe it? Anybody undecided? Yeah? This is 295. It goes down to zero at somewhat higher fluence, but okay, you need more fluence than at 100, but still goes down to zero. Really, guys, I'm the theorist here. I did nothing. Okay, I'm only explaining it. So we have metastable superconductivity. This thing still lives for many, many tens of picoseconds. Used 100 times more efficiently. I can't see anything, sorry. And it survives at room temperature not only with the penguins in Antarctica. Okay, so coming back to the beginning, and I'm almost done, I promise. What is a superconductor? It's a superconductor without resistance, expels magnetic fields. Well, I've shown you the more or less perfect resistance, but what about the field explosion? That's the nice thing. What about that? Is it really superconductivity? Well, these guys who cannot be here to give the talk and enjoy the beer, they have to be in the lab and measure it. And they're trying. So I can tell you they're trying as we speak. And we have to wait for the results. Alright, so I'm basically done. I've told you how to make a room temperature superconductor with light, but I haven't really told you anything, to be honest. If you want to learn more, come to the talk tomorrow at 10 in this very nice invited session. Most importantly, I should acknowledge the team that actually did the work. And I should also thank Chris and Damian, my students. Chris was the person who volunteered to bring me the Jägermeister before the talk. And cheers and thank you for your attention.
Thanks also for making sense of these laser pointers.
I tried.
So, does anybody not believe that one can make with light something superconducting?
Really, nobody? Where are the referees of the papers?
That's great.
Where are the referees of the papers? Not in the audience, apparently.
Okay, thank you very much.